So in section 2.8, we're going to spend some time with the derivative function. The derivative function, f prime of x, is going to be defined like this. It's going to be the limit as h approaches 0 of f of x plus h minus f of x divided by h. And if you're thinking, gee, this kind of looks like the limit of the slope of the secant line from section 2.7, you're right. This is exactly what it is. We're just doing it in general terms of x as opposed to specific terms of a equals 1 or a equals 2 like we did in 2.7. This still measures the slope of the tangent line. So it measures the slope of the tangent line. At any value of x. I should say at any value of x at which the function is defined. But we're going to have a sequence of steps that we're going to use to calculate this. It's going to mimic what we've done earlier. And let's start. The first thing we're going to need to do is we're going to need to find f of x plus h, this term here. And then I'm going to subtract things in the numerator. And I'll call that difference delta y. Then I'll divide by h. You should get that h in the denominator to cancel out. And then we'll have calculated this quotient. The last thing to do is to take the limit. So let's run through all those calculations. The first thing, like I said, is f of x plus h. So we're going to do that for problem number 22, which is f of x is mx plus b. So when we're all done, we're going to figure out how this function changes at any particular instant. So let me get rid of that here real quick. F of x plus h for this problem is going to be m times x plus h plus b. So let me squeeze that in here. That's going to be x plus h. So just plug in that in here for x. Now, we can distribute that and get mx plus mh plus b. By the way, what's the graph of y equals mx plus b going to look like? Yeah, it's just going to be a line, right? Mx plus b is just your general equation for the line. So we're going to find out how that line is changing at any particular point. The next step to do is to calculate this numerator. I'm calling it delta y out of convenience. Delta y is going to be f of x plus h minus f of x. Well, here's f of x plus h. That's right here. So I'll put that in. mx plus mh plus b minus f of x. I guess the thing that you have to be careful about here is this part. You have to subtract the whole thing. Now, when you're doing these things for the polynomial problems that we do in this class, this is always going to cancel. This second term here, this f of x, should cancel out completely. So b and b, those cancel. And I get some more cancellation. mx cancels. All right, not so bad. The third step is to calculate delta y over h. Basically, you're calculating this quotient now. You've got the numerator, that's your delta y, divided by h. And boy, were they all this easy? I'm sure a lot more people get A's in their calculus class, right? Does this one simplify a little bit? I think so, yeah. M. The last step is to calculate the limit of this. Limit as h approaches 0 of delta y over h. Now for us, in this case, it's the limit as h approaches 0 of m. Don't overthink this one. What's that limit? M. So that's my f prime of x. That's telling me how the function is changing at any particular instant. but it's not really changing much, right? It's just m. And that's because a line is just kind of steady. It's always changing with the same slope. No matter where you're at on the line has the same slope, so that's how it's changing. So it's m. So a little bit boring in that sense, maybe anticlimactic to do all that work and just to get m. Feels like we could have predicted that right here, right? M is just the slope of that line. So let's do one that's a little bit more challenging. This could be problem number 24. Hopefully that one will keep you a little bit more awake. Problem 24. F of x is 4 plus 8x minus 5x squared. We're going to play the same game with this one that I did with the last one. And I guarantee you this one will be a little bit more lively than just the linear equation we had for problem number 22. First step. Any takers? What's the first step? Perfect. Find f of x plus h. So it's going to be 4 plus 8 times x plus h minus 5 times x squared. So 5 times x plus h squared. We got a lot of simplification ahead of us. It's going to be 4 plus 8x plus 8h. Can we do this part in our heads? What do I get when I square out x plus h? Perfect. X squared plus 2xh plus h squared. And now I can distribute that negative 5. Please make sure you square it out like this. 4 plus 8x plus 8h minus 5x squared minus 10xh minus 5h squared. Whew. A lot of work there. I'll let you catch up, and I'll give you a second or two to shake out your hand, because we still got a lot to go. Next part, delta y equals f of x plus h minus f of x. Well, this whole big expression here, that's my f of x plus h. And f of x, well, I had that up here at the start. So let's calculate delta y then. Delta y is going to be 4 plus 8x plus 8h minus 5x squared minus 10xh minus 5h squared. All that's f of x plus h minus 4 plus 8x minus 5x squared. And you got to be a little bit careful here. You got to put this in parentheses. What was my promise to you last time when we looked at a problem like this? This term here, the f of x term, should completely cancel out. So let's see that it does. First of all, the 4's disappear. That one's easy. What else disappears? Well, we got an 8x and an 8x. Those cancel. Minus 5x squared minus minus becomes a plus. So that one's going to cancel as well. I'm running out of colors. Go for green then. Minus 5x squared and then the plus 5x squared, that cancels. Wow. That was the mother of all cancellations. What's left? Thank you. 8h minus 10xh minus 5h squared. So that's my delta y. Let's keep going. Third step. I want to calculate delta y divided by h. So that's going to be 8h minus 10xh minus 5h squared divided by h. Now, if this was an algebra class, I'd take the time to factor out the h and then carefully cancel it. But I'm assuming that you know that you can't just cancel it in one of these. You got to divide it out of all of these. I'm just left with 8 minus 10x minus 5h. Like that. Last step. I need to take the limit as h approaches 0 of delta y over h. Which is 8 minus 10x minus 5h. What's that limit? Thank you. 8 minus 10x. So on your exams, you can count on one that's going to work real easy if all you do is plug in the limit. Look for that. That's the first thing you try when you're working with limits, is to plug in the limit. And that's what works here. So that limit equals 8 minus 10x. And that limit is going to be your derivative function. It's going to be your f prime of x. F prime of x. Nice. Whew. Yes. Yeah. Yep, that's the way this one works. Now, I'm going to stick to just polynomials when I give you stuff like this on the test. If you were doing some of the homework problems, you would have seen some other crazy stuff. I'm going to have you do exactly one problem, kind of like 23 or 22, 24, something like that, like this. This is the long way. So this is like using a slide rule instead of a graphing calculator. In Chapter 3, we're going to try and make this process a lot faster, and we will. And you're going to get a lot better at this. You're going to be able to just look at these things and say, oh, okay, yeah, 8 minus 10x, that's easy. But we're not there yet, and do make sure you can do this kind of a calculation for me. But let me pause here if there's something that you're like, I went over that a little too fast, and you need me to help out in a certain spot. Here's a good chance. Let me ask you a question then. What does this tell me about the function? About the function we just looked at. What's that telling me about the function? All right. All right, so it's telling me some things about the slope. This tells me about the slope no matter where I'm at, right? Let's take a look at this function on our graphing calculators real quick and try and match it with what we see here. So, I'm going to put in 4 plus 8x minus 5x squared into my graphing calculator. Well, let's think of a good window. Let's go generously between maybe -8 and, I don't know, -8 and 0 should work. Now, I'm not really sure where to set the values in terms of the y direction, but there's a hack for that, right? Where's our little hack on that? Zoom 0, yes. Zoom 0 will adjust your calculator automatically. It looks like I should have probably chosen a wider window. Let me go a little bit to the right of the y-axis and maybe go out to 4. So, yeah. My max will be 5. Let's go down to 50. There. Okay. I still don't have the top of it. Darn it. All right. Last try. 20. Okay. So this is giving me, a good enough graph that I can figure out what I want to out of this. Now, this tells me the slope of the tangent line at any point. So in particular, let's pick a point to the left of the y-axis. So, I don't know, pick a value for x. -2, -1. When you look at the slope of the tangent line, what would you expect about that slope? Is it going to be positive or negative? Should be positive, right? So if we pick, say, for instance, -1, if I wanted the slope of the tangent line at -1, it would be f prime of -1. It would be 8 minus 10 times -1 gives me 18. Okay, it's positive, just like we expected. How about if we move farther to the right? Yeah, it should go negative, right? So if we pick, for instance, f of 2, f prime of 2, 8 minus 10 times 2 gives me -12 for the slope. And there's an interesting point in between here. There's an interesting point between where it's positive and negative. Can you see where that's at? Somewhere right around here. What happens to the slope of the tangent line at that point? Should be 0, right? So you can actually figure that out a couple ways. But one of the tricks you can do on your graphing calculator is you can hit the second key, then the calc key, and find, I don't know, a maximum. So we can kind of confirm where we think that maximum is. So it's going to ask you to set some limits. So I want to look for a maximum between this point and this point. So you can choose things. You can just type in a value like 0, and then maybe we'll go over to 2. So it's going to look for a maximum between those 2 points, and all I did is type them in. Now it's asking me for initial guess. I always just press enter at this point. The calculator is actually being lazy, and I get 0.800022, etc. What would you round that off to? What's approximately the maximum here? 0.8. And that actually gives us a way later on, we don't have to worry about it now, to find where a function has a maximum. Because where the derivative is 0, what's happened? The function has gone from increasing to decreasing, from positive to negative. And that's going to be where your maximum points are. So that's nice. Let's check it out here. If I put in f prime of 0.8, it'd be 8 minus 10 times 0.8, and bam, I get 0. Cool. So that's a maximum point. So that's nice that we can find those things with our derivative. Now, that's a little bit ahead of us, but you know, like any good storyteller, you do a little foreshadowing, right? So cool. Let's try and blend some of this calculation work with some of the work on our handout. And to do that, I'm going to start out with problem number 3, which is one of your homework problems, and I hope you forgive me for doing some of your homework. I know that you plan on relaxing over the weekend and doing some of these problems. I'm doing one of them for you. It's, you know, sorry. It's just a good problem. I want to look at it with you. So let's start with an easy one. And the idea here is we're going to look at a graph and try and picture how the function is changing and what that says about the derivative. So we'll start with a friendly one, b. And we want to look at how this graph is changing and think about the slope of the tangent line. So for b, we've got this part right here. And how's this function changing? It kind of reminds me of problem number 22. It's just changing in a constant manner, right? It's steadily going up. It's not going up faster or slower. It's just going up steady. And so the slope of the tangent line is actually going to equal the slope of this line. So its derivative should be this slope. Is that slope going to be positive or negative? It's going to be positive. So you're going to have a constant height at some value for y in your derivative. Let's switch over. What happens between these next 2 points? what's the function doing? Yeah, it's decreasing, right? So your derivative should have a negative slope. So when you're looking at the graph of the derivative here, between these 2 points, between this one and this one, it should be some negative value. And it's going to be a flat negative value because it's changing in the negative direction at a constant rate. Last but not least, the function is going up and up and up, again at a constant rate, right? So let's see if there's anything amongst our 4 possibilities that match that. Does it look like a possible winner here? Yeah, it looks like this one. Right here, and here, and here. Yeah, so the function was increasing at a steady rate, and then it switched over immediately to decreasing, and then increasing again. So, hey, this one goes with 4. Now let me do one other one with you together. I'll do the first one with you. And maybe not a bad way to go with this would be something like this. Let's start out with where this function has a derivative that's 0. The slope of the tangent line is 0. Can you see a couple points like that? Where would they be? Probably right here, right? Slope of the tangent line is 0. So call that maybe point A. This is point B. So at those 2 points, the slope of the tangent line has to be 0. Now to the left of this point, what's going on? Well, to the left of that point, as you're to the left of A with the values of x, the slope's decreasing. It's a negative slope, right? So your graph here should be negative. So it's going to be negative up till we get to this point, at which point it crosses the x-axis. You've got a slope of 0. And then, once we pass this point, what happens to the function? The function is going to be increasing. And it keeps on increasing until we get up to b. So the thing to see is that this is going to be above the x-axis until we get to b, and then it has to come back down to earth. And then it's decreasing after that. So that's kind of a rough sketch of its derivative. Does that match any of my choices here? Yeah, looks like it matches 2. Let's try this one more time with a different set of functions. And let me see here. No. Yeah. So this is actually problem number 16, I think. Let me just double check that. Yeah. What function do I have graphed here? A sine function, right? Now let's start with the easy places. Can you see some places where the derivative is going to be 0? Yeah, maybe right here. No, not right there. How about over here? Right here. Good. Every time, in fact, somebody said it real nice. Every time there's a maximum or minimum, the derivative is going to be 0. Because remember, the derivative measures the slope of the tangent line. So at a point like this, you're going to have the tangent line with a slope of 0. At a point like this, you're going to have a tangent line with a slope of 0, and so on. So at these points, my derivative is going to have that value. It's going to be 0. So, tell you what, let's light them up. At all those points, the derivative is 0. I'll give you a minute to convince yourself of that. Those are going to be places where the derivative is 0. Yeah, horizontal tangent line, that's the easy one. Now, the other possibility that I want us to think about is places where the derivative is 1 or negative 1. So for instance, at negative 2 pi, the slope of a tangent line there looks like it would be about 1. What would the slope of the tangent line be at negative pi? Negative 1. Positive 1, negative 1. So let me put in those points as well. Like that. Let me move this out of the way. Do these dots seem like they're forming a pattern? Yeah, it looks like a cosine function. Let's take a guess at a cosine function. Bam, if we put that in there. There's your cosine function. So it looks like the derivative of sine is cosine, right? I mean, it looks pretty convincing. If that's not too convincing, let's try one last one here. Let's try doing it kind of live. So what I have here is the graph of the sine function. And on this line, I've got a little cursor, which is showing you what happens to the slope of the tangent line. And as we move it, we're going to see how things change. So you can play with this. The link is out on D2L. If you want to take a look back at this and really understand what a derivative is, please feel free. That's why I created this. Now, what's the slope of the tangent line starting out here? 1. And as I move away from 0, well, there's the start of your cosine, right? Cosine of 0 is 1. Now, as I get closer and closer to this point here, pi over 2, what's going to happen to the derivative, the green graph? Should get closer and closer to 0, right? So let's do that. Let's go kind of go slowly here. And bam. There you go. So the derivative is no longer positive, and that reflects that the derivative means that this function is going to start decreasing. And it's going to keep on decreasing until you get to, say, this point here. Now, if it's decreasing, that means the derivative has to have what sign? Somebody make me look good. Lauren, if it's decreasing, the derivative is going to be negative. Thank you. So it should be negative for a while until I get down to here. And then the derivative is positive. It starts increasing again. So there you go. You can play with this as much as you want. You can actually change, I'm not sure if you can change the function too easily for yourself, but play with it. Try and get comfortable with the derivative. Let's go back to our handout. Any more comments on the derivative? You're getting a little bit more comfortable with what that means, I hope. Back here, when we looked at the derivative, I didn't really make much of a fuss about it, but right here at these endpoints, there's little circles on your graph, meaning the function is not defined there, right? That's what those hollow dots mean. So why would a function not be defined there? It's because the derivative isn't defined there. Why isn't the derivative defined there? Well, there's 3 reasons that a derivative might not exist at a point. And those are on the bottom of your handout here. The first one is if you have something which is not continuous. Now, if your graph has a little hole in it like this, that's called a removable discontinuity. So, okay, that's saying that, yeah, it's a problem, but, you know, it wouldn't be too hard to work around this problem. All you'd have to do is fill in that one point. So that's something that you can deal with. Whereas below, something like this is called a jump discontinuity. This is a bigger problem. This is like trying to get the Lions to the Super Bowl. All right, that's a huge jump, huge problem. But if a function is discontinuous, that could be a reason that you don't have a derivative. Now that wasn't the case up here. The problem with this one is you had a corner point. Remember that the derivative function really represents a limit. It's a limit as h approaches 0, all that stuff of fx plus h minus f of x over h. But what has to happen for a limit to exist? What two things have to equal? When you take a look at the limit. So it has to be continuous, and the limit from... Oh, you're making me look good. Bonus points for everybody. Well done. Yeah, the limit from the left and the limit from the right have to be equal. Let's take a look at something like this. Can you imagine what would the slope of the tangent line be here for the absolute value function to the right of 0? And it's going to be 1. And to the left of 0, negative 1. So when you're looking at that limit quotient for our derivatives, the limit from the left and the limit from the right aren't going to equal, are they? You're going to have 1 from one side and negative 1 from the other side. So they won't equal, so that's going to be a problem. The derivative wouldn't exist at x equals 0. And here's another example of something that wouldn't exist at x equals 0. I think that's x to the 5 halves, I think is that graph. X to the 5 halves equals y. I'm pretty sure that's that one, though. Now, there's one other place that you can see problems with a graph. And that's going to be this one, right here. You've got a vertical tangent. Well, there's nothing really wrong with a vertical tangent. I mean, those can happen all day. Can anyone tell me the equation of this orange line? Not the slope, but the equation. Thank you. X equals 0. All right. So, Evelyn, what's the slope of that line? Yeah, so the problem here is that the slope is undefined. So if you're trying to take the derivative of some function at a point where the slope is undefined, well, again, you're going to have problems. You're going to have a derivative which doesn't exist. So, at that point. Okay. So, flip things over to the back side. Problems number 42 and 44. Both of these have places where the derivative is undefined. List the x values for problem 42 and problem 44 where the derivative is undefined. Just let people... Thank you. So a lot of times what I'll do on a test is I'll ask you for the 3 places where a derivative could fail, or the 3 reasons a derivative could fail, and then I'll give you a problem like this and say, okay, here, find them. So I'm kind of leading you to this conclusion. Okay, so Alex, how about problem 42? Did you find a couple places where the derivative wouldn't exist? Yeah, at negative 1 and 2. Here, the function is discontinuous, so it's not going to have a derivative there. Here, the function has a corner point, so cool. Negative 1 and 2. Thanks. Let's see. Don't make Evelyn do all the work here. Someone give me the same points for problem number 44. Where would this not have a derivative? Negative 2, 1, and 3. So these two are corner points. This one's jump discontinuity. It doesn't have to be just jump discontinuity. It can be any kind of discontinuity. The function's not going to have a derivative at that point. So, nice. We'll finish it up with problem number 36 here. problem 36, let me show you the description of that in the text. So the table gives the number N of T measured in thousands of minimally invasive cosmetic surgery procedures performed in the United States. Wow, you know, I don't think I really realized that when I did this problem originally, that this number was in thousands. So that means that there's like 5.5 million, 10 million, 13 million cosmetic procedures in the United States. Wow, that's a lot of cosmetic procedures. In any case, I graphed that for us here. So it's on your handout. And, you know, the one thing that I want to work on first is, what does n prime of t represent? Now, n prime, or, you know, the derivative is always going to tell you the slope of the tangent line. But what does that mean in terms of the problem? Keep in mind the problem is in time in years here, so that's t. Time in years, and that's years past 2000. I didn't write the 2000 stuff here. I just left it as just the integers just above 2000. And then this is the number of procedures. What is n prime telling you? I mean, we can't necessarily calculate it directly, but you know, what would it tell you? The rate that it's changing, yeah. So the derivative talks about the slope of the tangent line, which measures how a function is changing. And since our function is the number of procedures, this is telling you how the number of procedures performed per year is changing. So the rate of change of the number of procedures. Is it 2 E's, procedures? Just one? Yeah. Procedures. Per year. Now that rate of change would probably be negative between 2000 and 2002. It dropped a little bit, but after that it's on a march upwards. If you were asked to estimate that rate of change for the year 2006, there's a couple things you could do. You could find the slope of a line between these 2 points, 2004 and 2006, or between 2006 and 2008. I actually wouldn't mind doing it this way, between 2004 and 2008. You know, it looks like it's a reasonable approximation. So that calculation would look like m prime would be, or see, m would be what? Let's see, we want 2008, so 10,967 minus 7,470 divided by 8 minus 4. I'm thinking it's around 700. Let's see, wait, no. Let's just calculate it. 750-ish, maybe? I don't know. Let's take a quick look here. 10,967 minus 7,470 divided by 4. So 874.25. So that's the slope of the tangent line, and that's that's the slope of the secant line. It's approximately the slope of the tangent line at that point. So it's not a bad approximation there. Okay, let me get you out of here and give you some homework. So for homework, try 1, A through D, 3, 9, 13A, 21, 23, 41 through 45, and 59. As always, those are just the odds, and that's section 2.8. Have a great weekend. See ya!